All right, so on problem 1, we have the prompt an oxide of nitrogen. So that means you have both nitrogen and oxygen inside this compound. And the main goal is to figure out the Lewis structure. So we want to know the Lewis structure, but first we need to know how many of each one we have. So I just know it is an oxide of nitrogen, so I just know it's N something O something, but we want to know how much. There's 2 hints that are given. The first one is that the total mass is 100 grams per mole, or the amount per mole. Then the second hint is that there's 1 gram of nitrogen per 3 grams of oxygen. Now, I did the long, complicated way, but there's a much, much easier way. The easiest way is just, okay, well, if you have 1 gram of nitrogen to 3 grams of oxygen, you just add the total. So 1 plus 3 is 4. So out of 4 grams, 1 gram of it's going to be nitrogen, or 25%. And you could do the same thing with oxygen. So 3 grams out of 3 grams out of 4 of oxygen, which then will give us 75%. And then if we know the total, 110, if we just multiply that by that over here and here, what will happen is that you'll get the percent mass of that. So 25% of 110 is about 28 grams, and 75% of 110 is about 82 grams. So this is useful, but we need to take a little step further. For us to compare how many nitrogens to oxygens, we want either molecules or moles. And since we have grams, we could change it to moles. So remember the molar mass, we want moles on top. So 1 mole of nitrogen will be 14 grams. And we could do the same thing with oxygen, 16 grams. So when you do that, you get about 2 and then about 5. So now I know I have N2O5. All right. To do the Lewis structure, I need to find how many bonds there are. So I'm going to use S equals N minus A, the number of shared electrons, the number of noble, if it was a noble gas, times minus the actual. So we have 2 nitrogens, 5 oxygens, so that's a total of 7 molecules. All of them want to be 8 for a full octet. Then we're going to minus the actual. I'm going to do it in steps. So we have nitrogen, which has 5, so 2 times 5. Oxygen, which has 6, so 5 times 6. And when we add that together, 7 times 8 is 56. 2 times 5 is 10. 5 times 6 is 30. So 10 plus 30 is 40. So that means they're going to share 16 electrons, or they're going to have 8 bonds between them. All right. In the Lewis structure, there's 2 conditions. No nitrogen, and no oxygen. So that kind of gives us, we have to alternate. Oxygen, nitrogen, oxygen, nitrogen, oxygen. You know, okay, I can't add another oxygen, so I need to add it somewhere else. I'm going to add it on the nitrogens. Okay, now technically this is correct. Okay, but we usually, things in nature like to be symmetrical. Now, does this exist? Yes, it does. But for our purposes for now, things in nature like to be symmetrical. So that is symmetrical. We have 1, 2, 3, 4, 5, 6 bonds, but we actually need 8, so we need to add 2 more. You could add them anywhere, but again, try to be symmetrical. The best answer is here, but you really won't know the nuances of that until later on. So if you put it there, here, or even here, I'll accept it. But the most likely structure is this one. And then we're going to put in the lone pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 lone pairs and then 8 bonds. So 24 plus 16 gives me 40. So that's the number I have. So I have the right number. So there is our Lewis structure of N2O5. In the next problem, it has the demo don't look. And this is when I burned magnesium and had it have a reaction with oxygen or it got oxidized. It needed an activation energy to get started, but once it went, it just kept on going. So we want to find the Lewis structure of these. And so I'm going to kind of go over it. So we have a metal and non-metal, so most likely it's going to be an ionic bond. Mg is going to have 2 valence electrons. Oxygen's going to have 1, 2, 3, 4, 5, 6 valence electrons, and we have technically 2 of these, so as a pair it looks like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, yeah. So by itself it looks like this. As a diatomic it looks like this. So this is the more correct form because this is kind of unstable, so that's why it forms this. It's going to react with magnesium to create Mg2 plus and then O2 minus. So 1, 2, 3, 4, 5, 6, 7, 8. And that's what happens. Magnesium being in the second column is willing to give up 2 electrons. Now it has a full octet on the inner rings or on the next electron shell down. For the oxygen it gained 2 electrons. So now it has a full octet. So that's how they'll look as that. And because this is negative to positive, we form an ionic bond. Here it's a covalent bond. Here it's just by itself a metallic bond. So that's that one. On the next one, it says for B, write an ionic equation for the redox reaction. This is when we have magnesium. Magnesium placed into iron 2 chloride solution. So we want to figure out what happens here. So we have Mg solid plus iron 2 plus chloride minus 1 aqueous. Now in a problem like this you just want to switch. So the 2 will go to here, the 1 will go to here. But you really don't have to write it like that. You just write it F2Cl2. Oh, sorry, FeCl. What did I do? Okay, FeCl2, and then aqueous. And then what's going to happen in this reaction? They're going to switch partners. Fe is now going to be the solid. Mg is going to be with chloride. It also has a charge of 2 plus, so it's going to be there. All right, so here it is. It is balanced because you have 2, 2, Mg, Mg. And let me see if we want a net ionic equation. So here, anything that's aqueous, you're just going to rewrite it as an ion. Mgs plus Fe2 plus Cl minus, but you have 2 of these. It's going to yield Fe solid plus Mg2 plus 2Cl minus. So here is my net ionic. And then I need to, actually this is a total ionic, and what I need to do is get rid of the spectators. In this case it's going to be chlorides. So I'm going to use a different color. Since I have 2 here, 2 here, they knock it out. So my net is Mgs plus Fe2 plus aqueous, Fe solid, Mg2 plus aqueous. So this is my net ionic equation for that one. All right, for the next one, problem C, we want to know the oxidations of PF3, PO4, 3 minus, and then P4. All right, so when we're talking about this, we're just looking at the relationship between the two. So phosphorus is bounded to 3 fluorides. So for each one of these fluorides, remember the 3 rules. Sum is going to equal the charge. Fluoride is -1. Hydrogen is +1. Oxygen most likely is 2 minus. So -1, 1 times 3. So fluoride has a pull of -3. That means phosphorus has to be +3 in this case. Oxygen is -2. So 2 times 4 is -8. The sum has to equal the charge, -3. So something plus -8 has to be 3, and that happens to be +5. So that's the case there. And when it's bonded to itself, the charge is equal, or the electrons are equally shared, so the oxidation state is 0 in this case. All right. Let's say you wanted to do IF2 plus. We want to find the Lewis structure of this one. So S equals N minus A. Noble is 3, so 3 times 8. They all have 7, so 3 times 7. So 24 minus 21. But it's a positive, so I'm going to change one of these electrons to, or get rid of one. So now we have 4 shared electrons or 2 bonds. So it's going to be, remember, symmetrical if possible. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we are done with, and then this has a total charge of plus 1. We also need to do another 2 more redox. You have nitric acid, which is HNO3, is going to react with copper and create NO2. We want to know if it's being reduced or oxidized. So here we have plus 1. Here we have -2. So 2 times 3 is -6. Charge is 0. Plus something. So 1 plus something minus 6 equals 0. So here nitrogen has to be plus 5. Here -2. -2 times 2 is -4. So here nitrogen is plus 5. You're going, oh, plus 4, sorry. Here you're going from plus 5 to plus 4, so you are gaining an electron, so GR, so that means it's a reduction, or being reduced. Okay. For the next one, you have magnesium metal. Is oxidized when it's being placed in chromium 3 nitrate, so NO3 minus. So now we have 3 of these, 1 of these. So CrNO3, 3. It's going to react with MgS. They're going to switch partners, so it's going to be Cr by itself plus Mg2 plus NO3 1 minus. So again, drop 2, 1. So Mg NO3 2. So I want to balance the equation. Here you have 2 of these, so we're going to put a 3 here to make a common multiple of 6, or yeah, multiple. Here we have 3 of these, so we'll put 2, then 2, then 3. Now it's balanced, and you want to write the net ionic. So 3 MgS plus 2 Cr 3 plus 6 NO3 minus 2 CRS plus 3 Mg2 plus 6 NO3 minus. So the spectator ions, and then there we have the net ionic. All right. So I kind of went through all of them pretty quickly, but hopefully that helps. Email me if you have any questions, and take care.